Hello and welcome. I've got a very special one for you today, starting with my video tracker. So I've maintained this list of cases, FMWC cases, MECC cases, MEWC cases for years to just keep tabs of which ones have I made videos on. And I shared an extract from it a while ago that some people have. The link is out there, but I don't know how many people actually used it, so that you could find, either find what cases there were or what cases there were by a certain author, or find my videos or whatever. But I've made a couple of upgrades to it recently, so I'm kind of relaunching the video tracker extract. So two upgrades. One is instead of just tracking my videos, it now has details of the videos by other people on the same case. So, here are videos by Lorenzo, by Ben, by Julian, and various others. And you'll see that for some of, like, for example, the Road to Las Vegas cases, there are many videos by many different channels. The second thing I've added is the number of free cases has gone through the roof lately. So I've added a column with a free case link. So for example, Harry released a bunch of introduction to esports training cases a few months back. So I've got the links for all of those in here. I did a video a little while ago on RV's Grinding the Grid case, on Harry Watson's Easy as Pie case, on Androni's Squid Game case, and there are a bunch more here that have been released. Not I haven't done videos on all of them, but you can see. So, for example, Cretaceous Park, I haven't got around to making a video yet, but Bo has done one, and Kobe has started making a series on it, and so on. So there's this tab that has all cases, and they're tagged by what competition. There's the FMUC is just a predecessor to the MECC, but Financial Modeling World Cup, Collegiate Challenge, Microsoft Excel World Cup. It goes all the way back to the model off things, and then we've also got this new category, which is pretty much only this year, of non-competition cases that people have just shared themselves. There's also a separate tab on it, which is only the free cases, and as you'll see, there's all the old model off cases are free, but then there were a few. I think Dan Mayo must have kind of requested that all the cases he wrote be free because his FMWC case is free, his Battle of 16 cases are all free. So good for you, Dan. There's a couple of FMWC open cases that are free, Card Game and Dominate the Dominoes. The finals of the two MEWCs, Eve and World of Warcraft, are both free. There was this like special event, the FMWC, that's free. The first kind of test round of the FMWC Brazil was free. But then, and the XL Ninja battles have been free. But you can see that, like, post model off, there were a handful of cases a year that were free, and now I think we're up to 20 free cases this year, and counting, because people keep throwing them out there, and it's super to see. So anyway, I decided. Well, first I decided that I would refresh this with kind of details of the free cases, and so that you can kind of easily find them here, because I realized a few weeks back I put together a playlist of all the videos I'd made that were on free cases, and they were kind of all ones that had come out in the previous few months, and I already had kind of missed a few, forgot a few. So I figured if we didn't get it organized, a bunch of these cases would just languish and get forgotten, which would be a shame because there's an enormous amount of work that has gone into them. So, having said that, yesterday's video was the Excel Shuffle, wherever that's gone. Here it is, which is available for free. And I decided, since I had just finished adding this and adding this, that I would make this free case week, and I'd try and fill in some of the gaps. So there's some here that, like first-person shooter, for example, I haven't had a chance to make a video on yet, but Bo has, so I'm going to make that lower priority. But there's these three, at least, that I'm going to try and have a go at, starting today with Sequencing LeeLoo, because I think it's probably easier than these other two, and I don't have a ton of time today. All right, that's enough chit chat. Let's get to the case, which is here. So the case is called Sequencing LeeLoo. It's by Karim Awenat, also known as DrKazza. I don't know if you pronounce it Kazza or Kaza. Anyway, DrKazza, let's say. Um, Karim is, I think, already qualified for the main draw for Vegas, and already qualified for the FMWC UK finals. So a very good player in his own right. I have tested a version of this case, but I think it might have changed a little bit, but something mostly like this. But it turned out he sent it to me with like a very humble message about, hey, would you take a look at this? It's maybe not ready. And I looked at it, I was like, oh my God, if I had realized it was this good, I would have recorded myself because it's actually a great case. But anyway, all right, enough chit chat. Let's dive on in. And I'm just going to zoom out a bit so the instructions can be on the screen. All right, you're a genetics researcher working in a sequencing lab. The perfect being LeeLoo has been delivered to your lab, and you're trying to decipher and match the gene sequences that are being read. A gene sequence is a list of the nucleotide bases that make up DNA. In the case study below, they're represented by a single letter. So it's adenine, cytosine, guanine, thymine. Just total coincidence that this and Cretaceous Park, which also featured, gene sequencing stuff, came out right around the same time. Some of the reads have the letter N. That's an error in the sequencing process, and no specific base could be identified. That's only used for bonus question 1. Following information is only relevant to bonus question 3, so we'll come back to that when we get to bonus question 3. I'm going to skip the bonuses altogether and start with the base count. So level 1, how many times does the base listed appear in the sequence given? So how many A's are in this? And this is a sort of classic Excel trick, which is first you substitute from here all the C's to blanks, and then you can measure the length of this and the length of this and see how much shorter did it get when you took all the C's out. So what does that look like? It looks like this, and these both work with arrays, so we can say len of this minus len of substitute of this by this to blank. And there we go. Okay, codon searching. Find the first occurrence of the codon specified. A codon is 3 bases in a row. Nucleotide bases are read in groups of 3 in genetic coding called a codon. Each group of 3 may appear multiple times in a read. Find the start number of the first occurrence of the codon. So again, this is a pretty standard Excel function. We're just going to search for this text in this text, and that'll give you, and actually those would both work fine with arrays as well. So let's do it just for lols. Okay. Level 3, stop searching. What is the first full codon before the first stop codon? The stop codons are shown in the codon table and are TAA, TAG, and TGA. So I think we'll come back to the codon table later, but let me just give you a quick look. So you've got all these triples here. So like TTT is fe. I don't actually know what that means, but TTC is also fe, TTA is liu, and so on. But these ones here are the stop codons. So TAA, TAG, and TGA are all stops. So for now, I'm just going to grab a spot. These are all very wide. Whatever, it doesn't matter. I'll put it here. TAA, TAG, and TGA, and I'll just name that stop. So the question is, what is the first full codon before the first stop codon? The one nuance that I do remember here is that you have to start your search after position 3. So in other words, if the first 3 characters were a stop codon, then there's not a full codon before that, so you have to search for the next stop codon. And same if this was, or if this was a stop codon, you don't have a full codon before it, you need at least 3 characters. So we have to find the stop codons in here, but from at least position 4 on. So we can say search for stop in here, but we want to say mid of this starting in position 4 and whatever, 999 should capture it all. So that will say this one is not found, this one is not found, and this one is found at position 52. And so if that starts at position 52, then we need to add 3 to that because we took off the first 3 letters, so that starts at position 55. Then the 3 characters that we're interested in would be 52, 53, and 54. So I guess we're actually just subtracting that off again. So we're only interested in the one that is not an error, and we can use tocol to get that. So say tocol 3 will drop all the errors. And then we want to mid this by that. So this is our starting position, the 52, and we want 3 characters. So that gives TGG, which hopefully matches. It does. So we'll cut that, bring it over here. And, oh, doesn't match that one. Oh dear. Why not? Okay. Whoops, because there are 2. Right, okay. So there are, let's just pull this back out. We'll start here. So on the search, I just, on the first one, there just happened to be only one non-error, so I just took that. But in this case, there are two non-errors, so when we two-call, we still have two values. So we also need to take the min of those because we're interested in the first position. So we'll take min of that, and there we go. A helpful example. Okay. Level 4, other strand codon check. Find the codon just before the stop codon on the reverse strand of the sequence given. Each DNA strand has a partner in reverse where A matches T, C matches G, and the strand is reversed. Okay, so let's first make the reverse sequence. And to do that, I guess we'll need a quick lookup table. So I'll have A, T, C, G going to T, A, G, C. And I'll just call that rev.lu, reverse lookup. So then first thing we want to do is reverse the characters here. So we can say mid of this. First thing you might know or might not, if I take a sequence of the length of that and 1, this sequence is going to give me the numbers from 1 up to the length of the sequence. So this is saying give me the one letter starting at position 1, 2, 3, 4, 5 up to the length of the sequence. So that gives me, oops, that's spilling because there's some other stuff below, but let's put it here. So this sequence starts with GGCAC, etc. And over here we get GGCAC, etc. So just a small twist on this to put it in reverse order. We can have the sequence start at the length and go in steps of -1. And now this sequence, instead of going 1, 2, 3, 4, 5, goes 199, 98, etc. So that flips it. So now it's ending GTG, just like this ends GTG, and then a bunch of G's, and then CT, and then a bunch of G's, and then CT. Yeah. So that's working. So now we've reversed it. Now we need to look it up in, what did I call this? I don't remember. Rev lookup. Column 2, 0. That flips them, and then we need to concat them back together. So that is our reverse sequence, and then we can just apply the formula from the previous level to the reverse sequence, hopefully. So that's going to say AAG, and then this is going to be wrong, and then I'll need to point it over here. No, still wrong. Okay. CTA at position 45 becomes tag. Position 54 in the partner strand. That's before this codon, just before the stop codon, yes. TGA, position 66. Okay. So we should find TAG at position 54. So yeah, right about here. The codon before TAG is AG, which I agree with. So what's, oh, hang on, wait. Ugh, yes, sorry, I just needed to move more than one reference. Stupid. All right. Silly, silly. Okay. Simple Hamming distance. Find the shortest Hamming distance between the string and the sequence. Look across the sequence and find the fewest number of changes to get the string to fit in the sequence. Don't try to insert or delete letters. We're just looking at substitution Hamming distance. So let's okay. So let's do this. Let's do mid of this by sequence comma len, and the comma here just puts it in the columns argument, which means it'll go across rather than down. Sequence of len that 1. So these are all the letters of that, and then I also want all the letters of this, the smaller string. So let's just start with a simple example. If we line this up against the first 21 positions of this, then we can say, okay, that's a match, that's a match. This would have to be changed to match. This would have to be changed, would have to be changed, would have to be changed, match, would have to be changed. So the Hamming distance is just saying how many changes would we have to make to get them to match. But so you can take a Hamming distance for the first position or the second position or the third position, you can basically slide the smaller one along and say, where is the closest match? So it's a sort of error checking thing. It's like you're looking for this sequence, but it's not here exactly. You want to find the closest match. So the way we're going to need to do that is to first let's just do a quick check. Are the lengths of all of these the same? Yes, the short one's always 21 and the long one's always 100, so then we don't need to make anything too clever. So what I want to get is, I want to get one row that's the first 21 letters of this, then another row that's from the second letter to the 22nd, then the third to the 23rd, and so on. So I want sequence of 21. So this is the numbers I want in the first column, and then I want to add 0 to that in the first row, add 1 to it in the second row, up until we get to 100. So we're going to say plus sequence. How many do we need? 80, I think, starting from 0. Oops, that's spilling because we have other stuff down there. So now we have 1 to 21 here, 2 to 22 here, 3 to 23 here, and sure enough, the last one gets to 100. So now we're going to take mid of this by that by 1. So that's giving us the first 21 letters, then the next string of 21, the next string of 21, next string of 21, and so on. Then we're going to compare that to mid of this by sequence, comma, 21, 1. And we can wrap that in a minus minus, turn those into numbers. So just like when we looked at the example, the two t's at the start match, then there's a bunch of things that didn't match, then there was one match, a bunch of things that didn't match. So this is the number of matches in the row. And sorry, I guess for the Hamming distance, we want the number of differences, not the number of matches. So let's just make that a not equal instead of an equal. And then we want to get the sum for each row of that. So we'll say by row that sum. And then we want the smallest of those. And sure enough, that gives us 12, which is what we were looking for. So we can take that out of there, put it in here. And that checks out. Okay, next, where are we going? Here. Complex Hamming distance. Find the shortest Hamming score between the string and the sequence. Scores are shown on the table to the right. Okay, so in this case, we're saying, before it was just, if it's an A matching with an A, that's no distance, but if it's an A matching with anything else, that's 1. Now we're saying, I guess an A to a G is a short distance. Are those the ones that were paired, A and G? I don't actually know my DNA very well. No, A and T were paired. Well, never mind. So, yeah, A and G are a short distance. T and C are a short distance. I'm sure there's a biology reason for that. And everything else is a long distance of 4. So the logic is going to be very similar to before. So I'm going to copy this down here, and let's just see if we can do it without any faff. Okay, so this is the one letter, this is the other letter. So instead of the minus minus, we're going to index on this grid, lock, X match the first letter against here, and they're written in the same order, so we can match them both against the rows, doesn't really matter. X match that against that, and X match the other letter, which is all of this stuff, against, no, just for completeness, we'll do it against the top one. Okay, so we're going to index this by match one letter against here, the other letter against there, all the different possible combinations. Then we're going to bi-row sum that. I think that is good. And sure enough, it is. Okay. Is there? No, that's it. 6 levels, sorry. Okay, bad reads. How many bases have been read as N in the sequences table of the gene sequence sheet? So this is basically the same as this level, except the one thing you have to watch out for is that you can't, I do remember this from when I did it before, these are whatever, maybe 100 characters long, and there are 1,000 of them. So if you try to concat them all together, it's too big. Oh my God, Copilot is back. Yeah, I think the limit on a calculated string is like 32,768 or something like that, which is fine because, like I said, len and substitute behave nicely with arrays. So what we can do is say len of all of these things minus len of substitute all of these things by n to blank, and close the len, and that will give us an array of 1,000 numbers, which is the number of n's in each one, and then we can sum across all of those. Okay, cat scan. How many times does the sequence cat appear in the sequences, column H only, of the questions excluding examples? Okay, so similar idea here. So we can say let sequences be vstack as a column H. So it's this one, this one, this one, this one, this one, and this one. I think that's it. Yes, that's it. Okay, so that's sequence, and then len can be len of sequence minus len of substitute sequence. Now you have to be careful here. If you substitute out cat, then it will get shorter by 3 characters for each cat. So a couple of ways you can handle this. You can either substitute it to blank and then divide this whole length by 3, or you can substitute something like that. Replace cat with ka, and then it gets 1 character shorter. Then I just want sum of ln. And that checks out. Okay. Okay, gonna do a re-record on the bonus because because I messed it up completely. So part of my feedback on the original bonus was that the original bonus was too hard. I think some of the wording of the original bonus by the 3rd DNA strand is still in there. So this is only one sequence in the gene sequence table is from LeeLoo. Using the instructions, work out. I think this should just now say work out which one it is. The 3rd strand doesn't apply anymore. So what do we know about LeeLoo? Only one match. You'll know it's hers because of the following. It has at least one of each stop codon. Those stop codons all align, i.e. their locations mod 3 are the same. So if you think about it, if the kind of genetic information comes in blocks of 3, if you have a codon at position 4 and a codon at position 8, then you got 4, 5, 6, 7 is just floating by itself. So it can't be part of a codon, can't be part of a multiple of 3. So if their positions are all the same mod 3, it means that what's in between them is a multiple of 3, which means it's a number of codons as opposed to just some blob. And given you know where the codons start, you can read the amino acid sequence that is created after the first stop codon and before the second, and that is boom. Okay, so let's do this. We're going to find out which of these is a match. So first we're going to search stop in here. And you'll see in some cases that returns errors, so these are not candidates. So just build this up. Let srb search. Then we'll say if or is error sr, then not all matches. Otherwise, otherwise we've got 3 numbers and we want to know, are they all the same mod 3? So then it'll be another if. We'll say if. So we'll take unique of sr, of mod sr3. So we'll take it mod 3, take the unique values of that, and we want to know how many rows that has. So if they're all the same, there'll just be 1 row when we take unique. So if rows of that let's say is greater than 1, then not aligned. Otherwise, we've got a potential match. And in that case, we want to figure out what's between the first stop codon and the second stop codon. So we'll say text before, text after, this, after stop, before stop. And that will give us some text, and we'll go and work with that in a second, but whoops, oh, I must have left some things in here. Oops, never mind. Boom. So we've got not aligned, not all matches, and then we've got a few things where there is a potential sequence. So for those potential sequences, we want to split that up into groups of 3 just like before, and then look those up in the codon table to see which one matches this. pro glue a la ser gli blah, blah, blah. So first, it would be helpful if the codon table looked more like a lookup table. So I'm going to flatten it out and then rewrap it. So to do that, I'm going to say 2row of this, because by sending it 2row, it automatically kind of reads like this. So these two end up next to each other, these two end up next to each other, these two end up next to each other, and so on. And then I can just wrap that in 2s, wrap rows of that in 2s, and we get this, which I will call codon LU. So now we can look up each 3 from that and return from here. And I'll tell you that one of the mistakes that I made on my first pass through of my recorded attempt was I took this code and did a lookup in here to convert that into a sequence and then looked for that sequence. But if you look, you'll see these are not unique. So many of these are LEU, many of these are SER. And so if you go from this to this, just with a lookup, you'll find one of many, many, many possible sequences that will translate to pro glue, ala, etc. So you got to do it the other way around. So let's come over here. We are going to say mid of this. Actually, sorry. I'm deep in an if now, so I can't make a new let variable. So let's start a new let. Let, I guess, I was going to say sequence1, but can't because that's a cell name. But let seq1 be that. Then I want to say mid of sequence1. I want sequence of len of sequence1 divided by 3, starting from 1 and in steps of 3, and I want to take the 3s. And actually, if I make this go across, then I won't get spill errors. So now I've got these spilling out here, which is good. Then I want to look those up in codon lookup. So we'll look up this in codon LU to 0. And now we can see this, and we can see that one of them matches, but let's just concat them all together so that we can see it clearly. And we're interested in this pro glue, etc. Which, yeah, I guess we can just look up. So we want to find the sequence, so we'll XLOOKUP that in here, returning from the sequence. Hooray. Yeah, the other thing that was kind of tripping me up was when this said about the third DNA strand. Like I said, that's from an older version. But so then I was trying to think, okay, is that we looked for what's between the first and second, so is that what's between the second and third, or do we have to flip it, or other things? But anyway, didn't have to do any of that. Just had to figure out which sequence matches. Alrighty, that's what I got for today. Like I said, it's going to be a week of free cases, so hope you join me for them. Thanks for Karim for this one, and for all of the many authors of the excellent free cases that the world now has. That's all I got for today. Thanks for watching. See you next time.